Welcome back to CS712. In this session I'm going to talk about DFA minimization. So let's back up and review why we care about minimization actually. So to generate a scanner, first the user provides us with a regular set, their description of the tokens they want to match. As we looked at earlier, we can take a regular set and we can construct a non-deterministic finite state machine from it. And as we also looked at earlier, we can take a non-deterministic finite state machine and construct the equivalent deterministic finite state machine. And this uses a subset construction algorithm, and that could cause a blow-up, a large expansion in the number of states. So step 3 is what we want to look at today, is because we'd like to not have any extra states that we don't really need. So today we'll look at this algorithm that actually minimizes the number of states required by the DFA. So we'll find, given one DFA, we'll find an equivalent DFA with the minimal number of states required to match the regular language. How does the algorithm work? Well, it's super aggressive. First thing it tries to do is let's try to use only 2 states. Right, one that models all the final states in the original machine and one that models all the non-final states. So we aggressively merge all the final states together, and we aggressively merge all the non-final states together, and we see if can we get away with just 2 states. And then you repeatedly back off that as necessary. So basically we'll split a state when the out arcs have a different destination in the merged DFA. So if the behavior can't be kept within one state, we'll split it off. Okay? And this algorithm produces the DFA with the provably smallest number of states required to recognize the regular language, which is a very nice result, right? We'll have the minimal machine that we need to match the language. So we'll look at this algorithm by example. Let's return to the conclusion of the earlier lecture where we were doing subset construction, right? We ended up with this machine here. And all I'm going to do is renumber that. But it's the same machine renumbered here. Okay. So we've got a machine with 9 states. Is that the best possible machine? Is that the smallest possible machine that would recognize the same language? That's the question. So again, let's run the algorithm. Step number 1 is let's be aggressive. Let's take the 5 final states in the original machine here. Right? 1, 4, 5, 7, and 9, and let's combine them all together into one state. And likewise with the remaining non-final states, we will combine them all together. And the question is, can we get away with that? The way we look at that is we'll study the behavior of the states by looking at the behavior in the original machine and look out what will happen in the new machine. So let's start out with state 1. Again, for now we've got state 1 combined with all these other states. But what does state 1 do on an A? In the original machine, it went to a non-final state. So I'm going to call all the final states state F. All the non-final states will be merged into state N. Okay, so state 1 on an A goes to N. State 1 on a B goes to 6, which is again a non-final state, so that would be state N in the new machine. And actually all the final states have errors on C. They just don't have an arc for C. So let's compare that to now what happens on state 4. State 4 in the original machine on an A goes to a non-final state. On a B, however, I'm sorry, state 4 is up here. On an A, we go to a non-final state. But on B and C, it's an error case, right? There's no arcs out of state 4 on a B or a C. So right off the bat, we can see there's different behavior for states 1 and 4. They're not going to be able to be kept in the same merged state. We're going to have to split off one of them. We look at 5. See, 5 goes to 2 on an A, that's a non-final state. It goes to 6 on a B, that's a non-final state. And again, on character C, it has an error. No outgoing arc on C. And 7 is the same way. A goes to a non-final, B goes to a non-final, and C is an error case. And 9 on an A goes to 8, which is a non-final, and 6, which is a non-final. And again, there's no outgoing arc on C. So we've done that analysis of the 5 final states, and we see that actually 1, 5, 7, and 9, so far, we can keep them together. But state 4 has different behavior on B, so it needs to be split off. Okay, so at the next step, we'll split 4 away. Before we do that, though, let's look at the non-final states. 2, 3, 6, and 8, again, we're aggressively combining them into one state. Let's see what happens with their behavior. Well, in their case, all 4 states in the original machine for A, it's an error, right? None of those 2, 3, 6, and 8, none of those states have an outgoing arc on A. So we just need to look at B and C to see if we can distinguish their behavior. State 2 on a B goes to a final state, state 5. Again, we're looking in the original machine here. And 5 is in our final set here. On C, state 2 goes to 3, which is a non-final state in our merged machine. State 3, again, we only need to look at B and C. State 3 on a B goes to 4, which is our final state. And C is a self-loop, which is back to a non-final state. So far, so good. 2 and 3 can stay together. Okay, what about 6? 6 on a B is an error state, however. Right, there's no outgoing arc in the original machine on state 6. So we end up with error here, which is going to distinguish it from 2 and 3. So actually we don't need to look at, well, we'll go ahead and figure out F. Go on and figure out what happens on C. So C on state 6 goes to 7, which is a final state. So again, it's distinguished from 2 and 3 also with regard to both B and C. Okay. State 8 on a B goes to a final state, and on a C, we're at state 8, we're looking at state 8, there is no outgoing arc on C, so that's an error case. So in fact, we're going to have to split off 6 from 2 and 3 and 8 from 2 and 3, and in fact 6 and 8 are different as well. So we're going to have to split them off as separate states. But 2 and 3 can be kept together. Okay. So we need to back off of this super aggressive and go to something like that. Right? We still got 1, 5, 7, 9 grouped together. We're hoping those will stick together. But 4 has been split off as a final state. 6 and 8 have been split off as individual final states. So now we have to redo the analysis and see if this will work. So back to 1, 5, 7, and 9. Again, the C is always an error case. On an A in state 1 in the original machine, it goes to 2. 2 is now in this 2, 3 group, which I'm labeling N1. So I'm going to put an N1 in there. B from state 1 goes to 6, which has been split off by itself. I'm going to call that N2. Okay. Looking at 5 now on an A, it goes to 2, which is in group N1. And 5 on a B goes to 6, which has been split off and is now called N2. 7 on an A goes to 8, which has been split off. It's now called N3, so we put an N3 in there. 7 on a B goes to 6, which has been split off. That's N2. And 9 actually has similar behavior. 9 goes to N3 and 8, and it goes to 6 on a B, which is now called N2. So in fact, we're going to have to split this state, which has 4 original states in it, and split it into 2 groups of 2 on the next iteration. Okay, what about 2 and 3? We don't actually need to look anymore at 4. It's been split off, so it can't be split anymore. And likewise, 6 and 8, we won't have to look at those anymore because they're already split as far as they can be split. But we do need to look at 2, 3 now. What happens with 2 and 3? Again, the A is an error case for these two, so we don't really need to look at that. But for B, from state 2 in the original machine, we go to state 5, which is in F1, the group of 4. And on C in the original machine, on 2, we go to 3, which is a non-final state. It's in this N1, this group, 2, 3. Looking at 3, however, if we look at B on 3, B goes to 4. 4 was split off, so now it's in F2. And now we have different behavior here with regard to B. So 2 and 3 actually are going to have to be split off in the next iteration. So our non-final states all get split back to themselves, actually. There's no nothing to be gained there. We can't combine any of them. So we got to do another back off, be a little less aggressive. This time we're splitting 2 and 3 apart, and we're splitting 1, 5 away from 7, 9. Okay, and let's check out whether this is going to work. So again, we don't need to check these singletons. They've already been split as far as they can be split. So we just need to look at 1, 5 and 7, 9. So looking at 1, 5, 1 on an A goes to 2. That's its own state now. So I'm just going to call those states their original names. 1 on a B goes to 6. 5 on an A goes to 2. 5 on a B goes to 6. So in fact, those can stick together. 1 and 5 still have the same behavior. 7 and 9, 7 on an A goes to 8. 7 on a B goes to 6. Again, 8 and 6 have been split off, so I'll just call them by themselves. And state 9 has the same behavior, actually. On A it goes to 8. On B it goes to 6. So in fact, this works. Those two sets of states can be kept together. And since we don't need to do any splitting, we don't need to do any more checking. And in fact, we've found the minimal machine. So let me just finish up by showing you that minimal machine now. Right, the minimal machine keeps 1 and 5 together and 7 and 9 together. So in fact, these two things can be collapsed because they have the same behavior. 7 and 9 can be collapsed because they have the same behavior. And I end up with a machine that recognizes the same language but has 2 fewer states, which the underlying proof demonstrates it has to be the minimal number of states to recognize that language. Okay, so that's the final step in actually constructing a scanner automatically from a regular expression, right? First you form the NFA, then you form the equivalent DFA, then you find the equivalent minimal DFA. All right, let's stop there.